Okay, so we have been talking about all the things in the 1D, right? But real systems are 3D, right? So if you have a sample of a semiconductor, it's not going to be 1D. I mean, there are now special, say, materials, the carbon nanotube, which can be turned into a 1D system. But in general, whatever devices you will have, they will all be 3D. You have a PN junction, it's a 3-dimensional device, right? You have a MOSFET, a bulk MOSFET is the 3-dimensional device. So all of them are in general 3D. So how do we extend all the concepts to 3D? So we can use similar concepts, but we'll have to draw our picture in the 3D. So I told you sometime back that all the unique wave functions can be contained within one Brillouin zone. So you can have several Brillouin zones. You can have, k ranging from -infinity to +infinity, but we can contain, because E as a function of k is periodic, so we can simply contain all of that information in one period, and that one period is -π/a to π/a. We call that as first Brillouin zone. And from the reciprocal lattice concept and all of that, we saw that the wave functions, the unique wave functions, you can obtain within one Brillouin zone. If I go to second Brillouin zone, it's just a repetition, right? It's going to give you the same wave function. It's not a different state. If I have a k and I have a k plus g, where g is the reciprocal lattice vector, I get the same wave function. We know that, right? So you can go back to your notes and check. So we can contain all the information in one Brillouin zone. So our Brillouin zone in the 1D used to be from -π/a to π/a, but in 3D, how do we create a Brillouin zone? So what is a Brillouin zone? Remember the definition? We have done it already. So what's the definition of Brillouin zone? So Brillouin zone is, I'm talking about the first Brillouin zone. So Brillouin zone, first of all, will be in the reciprocal lattice, right? Reciprocal lattice. Okay. So what is the reciprocal lattice? So if you have a cubic lattice and it has a unit cell dimension of, say, A, then the reciprocal lattice is going to be a lattice with unit cell dimension of 2π/a. If it is cubic, right? If it's a simple cubic. Okay, so that's your reciprocal lattice. And Brillouin zone is the Wigner seed cell of the reciprocal lattice. What is a Wigner seed cell? How do you draw a Wigner seed cell? So you pick up a point and you join that point with its neighbor, and then you start drawing perpendicular lines if it is 2D and planes if it is 3D. And the volume enclosed by all of those perpendicular planes will give you Wigner seed cell. And Wigner seed cell in reciprocal lattice is called Brillouin zone, first Brillouin zone. Okay, so how does a Brillouin zone going to look for, say, germanium or silicon or gallium arsenide? So we need to know its reciprocal lattice, right? If you know the reciprocal lattice, then we will be able to draw the Wigner seed cell, and that will be your Brillouin zone, right? But to create the reciprocal lattice, we need to know the direct lattice. So what is the direct lattice? What is the physical lattice for, say, germanium, gallium arsenide, or say silicon? What kind of crystal structure they have? They have a diamond crystal structure, right? So diamond crystal structure is it's basically made up of your FCCs, face-centered cubic lattices. So, okay, so if you have one face-centered cubic lattice, and along the diagonal, if you push another face-centered cubic lattice, right? So that will create your diamond lattice by 1/4 of the diagonal, I think. Okay, so that's your. So basically, primarily they are made up of your face-centered cubic lattices. You can kind of assume that. So what is the reciprocal lattice of a face-centered cubic lattice? BCC. FCC reciprocal lattice will be BCC. BCC will give you FCC. We have seen that, all of that, right? Okay, so we already know that the K values can be limited to the first Brillouin zone, and materials that crystallize in the diamond and zinc blend structure such as silicon, germanium, gallium arsenide, they will give you BCC reciprocal lattice. And how does a BCC reciprocal lattice going to look like? What will be the Wigner seed cell for that? How will it look like for the BCC? Something like this. Yeah. So this is the plane. So if you have a center lattice point here and you have a lattice point here, so this is the plane, that is the perpendicular bisector. Similarly, this and say this, right? So this is the plane that bisects, right? What about this plane? So this, and there will be a next, a cell, right? So the center of this and the next cell. So this is going to be the plane that divides that, and there will be a cell behind this as well, right? So you have this structure, looks like a kind of a football, right? So this is your Brillouin zone. Center of this Brillouin zone. So by the way, this Brillouin zone will be the same for silicon, germanium, gallium arsenide, which are the most important semiconductors for us. Most important is silicon. Gallium arsenide is also important. It has some applications in the RF and microwave, right? Germanium is also important for some application, but the most important will be silicon. Okay, so all of them have this reciprocal lattice. All of them have this BCC Brillouin zone. Now there are some points just for the nomenclature. So you see a point called gamma. So the center of this Brillouin zone is called gamma point. There are some other points as well. For example, so this is going to be a 1, 0, 0 type direction, right? Or 0, 1, 0. So your x is here, right? Y is here, so z is here. So this is going to be 0, 1, 0, right? So this point is called x point. Okay, so this is a unit cell in the reciprocal lattice, right? And the face, the center of the face is the x point. So there are several such points, right? So this, if I join this, so this is going to be this to this point, so this is your gamma L, right? So this is L point. Okay, so these are some points for the nomenclature, and they are coming from material science, group theory and all of that. We won't go into the details of these, but some of these nomenclature can be useful for us. For example, this gamma point, this L point, X point, they are important. So why I am drawing this? Because these directions that I am drawing, they can be important for us. So there are several high symmetry directions that are important for us. Why they are important? Now you have this whole K space, right? All your K values are inside this. Okay, so what is the, by the way, spacing between the K points? So now you will have K1, Kx, Ky and Kz, right? You won't have one K, you have Kx, Ky and Kz, and each of the K will be discrete. So for example, Kx will have spacings of 2 pi by Lx. Capital Lx. Capital Lx is the dimension of the sample in the x direction. Similarly, Ky will have a spacing, it will be discrete, of 2 pi by Ly. Ly is the length of the direction, length of the sample in the y direction. Similarly, 2 pi by Lz for Kz. Okay, so there are several K points here because 2 pi by L is kind of a small number. So, okay, so what is the extent of, can you tell me what is the dimension here? What is this? If I have, say in the direct lattice, the unit cell dimension is A, what is this then? Do you remember? In a simple cubic, if you have A, what will be the reciprocal lattice? 2 pi by A. Right? So this dimension will become 2 pi by A. In the reciprocal, I mean the simple cubic will remain simple cubic, but the length of the unit cell will become 2 pi by A. But in case of BCC and FCC, you can go back and check your notes. It becomes 4 pi by A. Okay, you can go back and check. So that will be, so this is going to be 4 pi by A, where A is the original unit cell dimension in the direct lattice. Okay, now you have this 4 pi by A here. Now compare that, so 4 pi by A. Now compare this with say 2 pi by L, say Lx. Right? 2 pi by Lx. So here you have the length of the whole sample, and here you have small unit cell dimension. Which one is going to be larger? This is going to be much larger than this. 2 pi by Lx. 4 pi by is going to be much larger than 2 pi by Lx. Okay, so this dimension is still much larger than the spacing between the k points. So there will be several k points that you can fit inside this volume. What will be the total number of by the way points? N, total number of atoms. In one Brillouin zone you can fit n values, which is equal to the total number of atoms in the original crystal. And total number of atoms are a lot, right? Per centimeter cube in silicon you have 10 to the power how many? 22 roughly. Okay, so there are a huge number of k points inside this volume. Okay, so all of those k values are possible states for us. Every k value, so now it's going to be a vector. So say I have one k point here, it means it's going to be a vector with kx, ky and kz, kx I cap plus ky j cap plus kz k cap, right? So every point in the space inside this Brillouin zone is a state for us, and every point is going to give us a unique block wave, right? Remember the block wave function is equal to u of x, which is some periodic function, into e to the power iota kx. Used to be iota kx in 1D, but in 3D it's going to become iota vector k dot vector r. Okay, so one k point gives you one block wave vector. It means it's a one quantum state. Every point inside this is one quantum state, right? So when we are counting our states, we are going to count them within this three-dimensional volume. We will be doing that. Okay, now you have all of these k states and you have all of these block waves. Each k state is associated with some energy also, right? We are talking about block waves. Block waves are energy eigenfunctions. Every block wave is going to be associated with some energy, right? It has some energy eigenvalue. It is an energy eigenstate, right? So energy eigenstate will have some energy associated. So each k point has some energy. Okay, now when we talk about the conduction band minimum and valence band maximum, what kind of points we are looking for? We are looking for maximum energy and minimum energy points, right? So these high symmetry directions are important because along these directions there will be a point k for which you will have either energy maximum or minimum. So the extrema points occur along these high symmetry directions usually, at least for this silicon, germanium, gallium arsenide. So these directions are important because along these directions you can have these maximum or minimum energy points. Okay, for example, in case of silicon you will find that the energy minimum occurs along gamma x direction. So at some k it will be minimum, right? So you have several of these k points and you need to pick which k has the minimum energy, and those minimum energy points for the silicon are going to occur along gamma x direction. So you have one gamma x direction, but equivalent direction is, this is also equivalent direction, this is also equivalent, this is also equivalent, this is also equivalent, this is also equivalent, right? So this is a 0 1 0, but we know that 1 0 0 0 1 0 0 0 1 0 1 bar 0, right? 1 bar 0 0, all of these are equivalent directions. So if there is a minimum of energy along, say 0 1 0, there will be also a point which will give you minimum energy along, say 1 0 0 or 1 bar 0 0, or there will be 6 such directions which will give you minimum energy. Similarly for germanium, similarly for gallium arsenide, but gallium arsenide, it's a special case. We will see that for the gallium arsenide the minimum energy point occur at gamma equal to 0. So you don't have to go to direction, so it's just one point. Okay, so these high symmetry directions are very important for us, and it's just a nomenclature, right? So L points are along 1 1 1 direction. So I have put a bracket, this type of a bracket here. It denotes set of directions, set of 1 1 directions, right? Equivalent. So when you put this type of brackets, it means equivalent 1 1 directions. It means 1 1 1 1 1 bar 1, right? 1 bar 1 1 1 1 1 bar, all of those directions. In total there will be 8, right? Similarly x means zone and along 1 0 0 direction, all possible 1 0 0 directions. Okay. And this you can of course find out, you know, gamma to L distance, for example, this to this point distance is 3 by 2 root 3 by 2 times gamma x direction. This will become important when we are trying to find out where our conduction band minimum is. Okay. Okay, now let's try to draw the EK diagrams for some real material. So we have seen EK diagrams, right? But for perfect periodic crystals in 1D, so our system was very you can say simple. Now real materials are not that simple. Real materials will have 3D. We are still assuming there is no defect or anything like that. We are still talking about the ideal, but it's in 3D, and you have complex atoms. So it's not just that. So you have this atom which can contribute, say, 1 electron only, right? So we made all of those assumptions, right? So we assume that our crystal lattice have all of these atoms that can only contribute, say, 1 electron. But you have now real atoms like silicon, which has valence electron and its outermost shell has 4 electrons. Okay, so you have these real atoms with real energy states. So the things become complicated. Okay, so now you have 3D, so you have Kx, Ky, Kz, right? So K has these 3 components, Kx, Ky, Kz, and if we want to relate this to energy, so you will need a 4-dimensional space. 4-dimensional space you can't draw, right? You have Kx, Ky, Kz, and you have to draw a relationship between Kx, Ky, Kz and E. So it's a 4-dimensional relationship. So we can't draw that. So what we do, we try to simplify the things. Now we know that we have these high symmetry directions like 1 1 1, 1 0 0, which are important for us, along which you can get energy minimum or maximum. So we only draw our EK diagrams along those directions. So when you draw EK diagram along a particular direction, then it becomes 1-dimensional. Okay, and that's what usually we do. So real material, some example I can give you. So this is the EK diagram for some real materials. So on the leftmost it is germanium, then you have silicon, then you have gallium arsenide. Okay, it's a EK diagram for a real material. And you can see some directions here. So this is a gamma x. It means this part of the EK diagram has been drawn for gamma x direction. Now what is the gamma x direction? It can be 1 0 0 0 1 0, all of them are equivalent, so collectively we are writing 1 0 0, right? So it means positive, negative, and also this all possible 1 0 0 direction. If you draw EK diagram along those direction, so that will look like this half part. To save the space, what we do, we draw EK diagram along another direction also. So this is not the same direction. So don't think this is the negative part of this. No, it's not the negative part of this. Negative part of this is going to be this only. Okay, it's just going to be the reflection of that this part. To save the space and to put the most information in the same space, what we do, we draw EK diagram along gamma L direction. So this is 1 1 1 direction. Okay, and this part is for 1 1 1 direction. So these are two high symmetry directions along which you can have some minimum energy points. Now there can be several minimum and maximum energy points, and you need to choose. So what is the definition of the valence band? It is the highest possible filled energy band at absolute zero. Absolute zero temperature. When my temperature is absolute zero, the highest filled band is my valence band, and the lowest empty band is my conduction band. Okay, now from that definition, look at this. So you can see several such curves, right? So they are not exactly parabolic, that we draw bands like this. They don't look like this, but similar, right? Around the minimum and maximum energy points, you can see they still have some kind of a parabola. For example, here, right? So this is still a parabolic kind of. You can use some parabolic approximation here. Similarly, here you can use. Okay. So let's talk about the valence band. Which one is the valence band? Which one is the conduction band? Can you tell me? See, if I look at this, which one is the valence band? Which one is the conduction band? So this is the valence band, right? I mean, all of these candidates can be valence band, but which one will I take? So I have this branch also, I have another branch also, right? At k equal to 0, which is gamma point, both of them are giving me the same energy. So this is the energy axis. So this is when you have two k values that give you the same energy, it means it is degenerate. So gamma equal to 0, you have two bands that are degenerate, and then there is another band which is called split off band, because it's slightly split from this energy value. But the valence band is going to be this. Okay, so because this is the highest energy band. What about the conduction band? So you have several minimum. This. So these are valleys. Several valleys are there. Which valley is the conduction band value? This one. This is the lowest one. Okay, so for the germanium, the conduction band minimum is occurring along the gamma L direction and at the L point. So this is the L point. L point, what is the L point? This. So for the germanium, the valence band, the conduction band minimum is here. So this is that K point that gives you the minimum energy. Okay, so this is going to be the minimum energy point. This will also be minimum energy point because that's equivalent, right? Similarly here, right? Similarly there will be eight such points that will give you minimum energy. Okay. What about silicon? So silicon, again, for the valence band you have similar type of, these two branches are totally merged here, right? You still have a split off band, but the difference is much smaller. So you have this and then you have several minimum also. So this is the valence band. What about the conduction band? So this is the conduction band. Okay, so lowest energy value. But this is not along the gamma L direction, this is along gamma X direction, 100 direction. Gamma L direction is 111 direction. Okay, gamma X direction is 100 direction. And the gap between the lowest energy point and the highest point here, that is your band gap. This is Eg. For silicon, it's going to be 1.12 electron volt roughly. Okay, for gallium arsenide, it's a special case. For gallium arsenide, you have that the same valence band at gamma equal to 0, right? Gamma equal to 0, but the conduction band minimum is also at gamma equal to 0. Okay. So the electrons, if you have in the system, you saw that they tend to occupy the minimum. They tend to occupy the states that are around the minimum of the conduction band edge. Similarly, holes try to occupy the states which are at the maximum of the valence band edge. Okay, so if you have electrons, most of them are going to be here. If you have holes, most of them are going to be here. Similarly, most of the holes are going to be here, most of the electrons are going to be here. There can be some electrons at higher energies, but their probability is much smaller. We will see the probability of occupancy of states also, but to reach very high energy state, they will have to have some external excitation. Okay, at room temperature, it's not usually possible. Okay, so let's talk more about this valence band, and then we'll talk about the conduction band. So for the valence band, what you first of all you see that for the valence band occurs at k equal to 0 for all the three cases. It means it occurs at the gamma point, and then you have these three branches. Two of them are degenerate. Degenerate means they have the same energy. One of them is split off. Okay, let's look at these two degenerate states. So both of them will have holes, but which one has the higher effective mass? Can you tell me? I have two branches of my bands here. Which one has a higher effective mass? Can you tell me? So you have two curvatures. One is like this, one is like this. If you zoom it out, it is this. Which one has a higher effective mass? I'm talking about the magnitude, don't talk about the sign. Of course, the sign of the effective mass is negative here, right? It's a valence band. If you have a negative curvature, it's downward, right? So the curvature is going to be negative. It's a downward parabola. But magnitude wise, which one has a higher effective mass? Lower curvature. Which one has a lower curvature? The upper one, right? So effective mass is inversely proportional to the curvature. And which one has a lower curvature? This one. So lower curvature will have a higher effective mass. That's why this band, it's basically called sub band, because you have two bands with the same energy, so it's called sub band. Okay, so this sub band will have a higher effective mass. It's called heavy hole band. Similarly, this one, which has a lower effective mass because it has a higher curvature, it is called light hole band. Okay, this band which is split off in energy, it's called split off band. And we will usually not talk about it because most of the holes are going to be here. Okay, so there is some description I have given here, you can check. Now let's talk about the conduction band. So for the conduction band, you can have again several such energies, several such minima, but the minimum point is going to be your conduction band. And unlike the valence band, you don't have these sub bands here. Okay, so let's look at gallium arsenide a little more closely. because this is a semiconductor which has the conduction band minimum and valence band maximum at the same point, same k vector. So the energy band looks like this, right? You can now see the zoomed version of these branches, and they are degenerate here. Then you have split off, and then you have these valleys, different valleys. Okay, so you have one valley along this gamma L direction, L6, and then you have also this delta 5, another valley which is along delta X or delta X direction, and then the minimum is at delta equal to 0. So this is the conduction band minimum, and the band gap is around 1.42 electron volt. So little higher than the silicon. Gallium arsenide has a little higher band gap than the silicon. So more is the band gap. You will see later on that it will be more useful for high power applications. Okay, larger the band gap, you will have larger breakdown voltage. So that's why gallium arsenide can be used for higher power applications, say RF and all, power amplifier. Okay, some more observation. So this is gamma equal to 0, gamma point with k equal to 0, and this is also k equal to 0. So this type of semiconductors which have the conduction band minimum and the valence band maximum at the same k point, they are called direct band gap semiconductor. Okay, if this point and this point are not at the same k, they are called indirect band gap semiconductor. So direct band gap semiconductor and indirect band gap, we will revisit them, but this type of band, if they have direct band gap, then they have a unique property that they can emit light. Okay, and silicon is indirect. You saw silicon, for silicon valence band maximum and conduction band minimum, they were not at the same point. So for silicon it's not a direct band gap, it is indirect band gap semiconductor, and that's why silicon does not emit light as such. What's the reason we'll see later, but for the time being you can just see the characterization of how we characterize the direct band gap, indirect band gap. Okay, in addition to this gamma 6 point, which is the conduction band minimum, there is another L valley minimum which is just 0.29 electron volt above the gamma valley minimum. So this one. Okay, so this is 1.71, this is 1.42. So most of the electrons are going to be here, but because this valley is just a very small energy above this valley, there can be some electrons that can occupy energy states here as well. It is possible. Okay. What happens is, when you apply a high electric field, electrons that are there in this valley, the gamma valley, they can get enough energy from the electric field and they can move from this to this. Okay, although it's at higher energy, but they can get energy from the electric field, they can get accelerated and they can reach this valley, from this valley. So there can be a transfer of electrons from gamma valley to L valley. Now that leads to a negative differential resistance. That can give you a negative differential resistance. Negative differential resistance means if you increase the voltage, usually what happens? Your current increases. Okay, but in this case, what will happen when you increase the voltage? The current will decrease. So that means it has a negative differential resistance. And why this happens? It's because they have different effective masses. Look at this effective mass and look at this effective mass. Which one is higher? Which one is lower? This has a larger curvature. Larger curvature means lower effective mass. This has a higher, less curvature. It means it has a larger effective mass. This is, the particle becomes heavier here. The particle is lighter here. Which one will be easier to move? Which one will have a larger mobility? This, because it's light. If you apply an electric field, a light mass is going to move more freely compared to a heavy mass. Yes? So you increase the electric field, your current increases when the electrons are here. So they are light, they have some mobility, they are moving. But some of them at high electric field start to move from here to here. They become heavier. As you increase the bias, the electrons are becoming heavier and heavier. Although you are applying an electric field, but electrons are moving to another valley and they start to become heavier and heavier. So that effect can give you a decrease in the current, because they are becoming heavier, their mobility is decreasing, that leads to a reduction in the current. Okay, so this type of effect can be used for making microwave devices, like there's a device called gun diode. Okay, I don't know how many of you even know about that name, but it can be used to make some microwave oscillators. Okay, so let's start with the new topic, constant energy surface. So we all know about the EK diagram. It's a relationship between the energy and the K vector. But there is another way to represent the same relationship through the constant energy surfaces. So what a constant energy surface is, as the name implies, it's a surface at which the energy is going to be constant. So it's basically all the points, all the K points for which the energy remains constant. I mean, energy can be a given energy, say some E1, and I'm going to find out all the points, the plot of all the points for which my energy is E1, right? So the simplest example can be 1D. So EK diagram is going to be something like this. Yes. Now I know that for this particular energy level, say this is E1, these 2 points are my K points for which E is equals to E1. You won't find any other point for which E is equals to E1, only these 2 points. So although in 1D it's not a surface, there are just 2 single points, discrete points, but in general I will say yes, these 2 points make my constant energy surface. Okay. Situation becomes a little complex when we go to 2D and 3D, but let's start with the 1D. Yeah, so as I was saying, so this is an alternate way of representing the EK relationship and consists of plot of all the allowed values of K for which the energy is constant, say E1, E2, E3, whatever. So let's start with the 1D example. Now in 1D, we know that around the energy extrema point, whether say energy minimum or energy maximum, my EK diagram can be represented as a parabolic approximation. Okay, so it's an approximation, so you don't take higher order terms, but you terminate the EK relationship up to second order. You keep some non-linearity still, but don't go to the higher order, because most of the time your EK diagrams are going to look something like this. It can be more complex, but around the minimum energy, if I just constrain myself to say a very small value, a small range of K around the minimum or maximum energy, then I can say that this curvature that you see here, this one, so that is approximately parabolic. Okay, so that's what we are going to do. So something like this, right? So say the minimum energy, I'm taking the example of minimum energy right now, you can take maximum also. So say minimum is the E naught, and this will be parabolic. Yes. Now in this example I have taken K equal to 0, the minimum energy is at K equal to 0, but it may not be the case necessarily. It can be at some K equal to K naught. Yes. So it can be something like this. In general, this is the most general case you can say. So when my K is equals to K naught, energy is E naught minimum energy, and this is what my parabolic approximation will look like. The most generic case. Yes, this valley can be present at some K equal to K naught. Now how am I going to represent this relationship? If this is a parabola, how will my EK relationship approximately look like? mathematically. So it has to be some second order. Yes, second order expression. So in general, I can represent it as E minus E naught is equals to approximately A times K minus K naught squares, where A is some constant. Okay, so at K equal to K naught, E becomes equal to E naught. Yes, K equal to K naught, so this becomes 0 and E becomes equal to E naught, and this square is because of the parabola. Now let me call this K minus K naught as some K1. So K1 is basically the distance measured from the minimum. So for example, the K is here, right? K naught is here. The difference between them is K1. Got it? So this is the distance from the minimum energy point or maximum energy point, extrema point. Okay, so this is a simple relationship then. E minus E naught is equals to some A K1 square, right? Now I can also represent, because this is parabolic approximation, I can also represent this relationship in terms of effective mass. So what is effective mass? So proportional to 1 upon d2 E by dk square. Yes. So if you calculate, because this is perfect parabolic relationship, so you will get this A in terms of effective mass. If I calculate 1 upon d2 E by dk square, I think it is h bar upon d2 E by dk square, or whatever the formula is. So then you can get this A in terms of the effective mass. So eventually you get E minus E naught is equals to h bar square divided by 2 m star is the effective mass, into K1 square, where A is equals to this h square upon 2 m star. You can get that again from the definition of the effective mass. Okay. Now I have this relationship. It looks familiar, right? We have seen this many times, that E is equals to some h square K square upon 2m for the free particle, for example. Yes. So something similar we get. But m is replaced with the effective mass, m star. Now this is the 1D. What about the 2D? 2D is a little more complex, but you can use the same parabolic approximation in 2D just as an extension of this. So in 1D you have A K1 square. In 2D you will have one more term because of the 2 dimensions, right? There will be K1 and K2. So it will be A K1 square plus B K2 square. In 2D it is this approximately. Only around the extremum point, either minimum or maximum. Yes. Now similar to the 1D case, I can represent these coefficients by 2 effective masses, not one effective mass. So corresponding to the K1, there is an effective mass m11 star, h square upon 2 m11 star. Corresponding to B, there is another effective mass m22 star. Okay, h bar square upon 2 m22 star. Yeah. So they can be calculated as by taking the second order derivative of energy with respect to K1 and K2. So del 2 E by del K1 square, that gives you this m11, and similarly del 2 E by del K2 square, that gives you this. Got it? So you have different curvatures in different direction. In 1D you can very easily see the curvature, but in 2D the curvature may be different in different directions. So, but by the way, what is this equation? Say if my E is constant, I'm talking about the constant energy surface, right? So in 1D it is just 2 points. We saw that. In 2D, what will be that? So if E is constant, this is an equation of what? Constant equal to A x square plus B y square. What is this equation? What? Ellipse. This is an equation of an ellipse. Yes. If A and B are different, this becomes an ellipse. So it will look something like this. Now at this ellipse, any point if you take, that will give you the same energy. So constant energy surface becomes this ellipse, right? So say this is my K1 right now and this is K2. So this point, all of them will have the same energy E. Okay, if you say draw it for a different energy, say if I increase my energy, so then you will get a bigger ellipse. Okay, so the characteristics of an ellipse is that it has a longitudinal axis and a transverse axis. Okay, so K1 is along the longitudinal, K2 is along the transverse. It could have been that this would have been the longitudinal and this would have been transverse. I mean, it depends really upon the coefficients A and B, right? So they depend. They decide what is the major axis, which one is the minor axis of the ellipse. So by looking at these equations, can you tell me? So is M11 larger than M22 or M22 larger than M11? So this length is small, this length is large, right? So I can calculate this length by putting K2 equal to 0, right? So then K1 becomes this length, correct? So K1 is equals to then what? 2M11 star into E minus E naught divided by H bar square under root. Yes? And similarly, K2 you can calculate. So K2 for K2, K1 will be equal to 0. I mean, let me call this K1 dash and K2 dash. So K1 dash is this point and K2 dash is this point. Right, so this will be 2M22 star into E minus E naught divided by H bar square. Now, larger the effective mass, larger is the axis. So the major axis, so M11 is larger compared to M22 because this is large. Yes, and this is the small one, right? So it is under root of M22 dependency. Because of that, you can get different axes. Okay, so this is M11 is larger, M22 is smaller. So whenever you have a larger curvature, so this is more curved than this. Yes, so you have a larger effective mass here. Okay, I'm not talking about the curvature of E versus K. I'm talking about this curvature and this curvature. Okay. So this is your 2D. Now you can extend the same concept to 3D, which is the one which is important to us. We are going to be talking about the properties of the bulk silicon. So bulk silicon is 3D. Yes. So for the 3D, what do you have? You will have A K1 square, B K2 square plus C K3 square. Again, about the extremum point, either minimum or maximum. Now the sign of A, B, C, it can be positive or it can also be negative. Okay. So it depends upon, say for example in the valence band, you have an inverse curvature. So in that case, effective mass is negative, you know that, right? So in that case, the coefficient may be negative. For the conduction band, coefficient will be positive. So you have A K1 square, B K2 square, C K3 square, and correspondingly you have 3 effective masses, M11, M22 and M33 for 3 different directions. Yes, simple extension. And again, K1, K2, K3 are all measured from the extremum points. They are not the K's. Okay, they are the distance from the extremum point. So say if you have this point in the K space as say the extremum points, let me call this as some vector K naught. In 3D it will be a vector. So these 3 will be measured from this. So it will be this, 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 right? So that's what I'm talking about. So measured from the extremum point. Okay, actual K is, say, actual K is not K1, K2, K3. Actual K will be some vector K naught plus vector, say, let me call this K dash. So K dash is composed of this K1, I cap, K2, J cap, K3, K cap. You got it? or just don't make it too complex. If you don't understand it, that's fine. Just always keep in mind that this distance is from the extremum point k1, k2, k3, not from the origin. Okay, so we have this simple relationship again. Now let's take this E to be constant now. In 2D it was an ellipse. Now in 3D, what is this equation? If I have an E is equals to constant is equals to a k1 square plus b k2 square plus c k3 square. What will be like, I mean, what is the shape? So in 3D it will be 3D version of the ellipse, which is ellipsoid. Okay, so in 3D it will be ellipsoid. So basically you have an ellipse and you rotate that in the 3D, so you know it becomes like a distorted sphere. Yeah, so that's your ellipsoid. Okay, now let's take an example, say for gallium arsenide. So for gallium arsenide conduction band, you have only one minimum energy point. So so in the gallium arsenide, the energy band diagram, if you look at EK diagram, not the energy band diagram, sorry. If you look at the EK diagram, the minimum energy point is at the gamma point. So you may remember that. So there was this valence band and then you had the conduction band, and this was the gamma point. Okay, there were different points, gamma point, you know, L point, the different values. So this, now at gamma point, what you have, so gamma point is at the center of the cubic lattice. So that's what the gamma point was. Because of the perfect symmetry at the gamma point, what happens if I move a little away from the gamma point in the reciprocal lattice, so it gives me an isotropic environment. Isotropic means if I move in any direction, basically I get the similar environment. Okay, so because of the symmetry of this gamma point, if I write down this relationship, so then this M11, M22 and M33, because of the isotropic nature of the gamma point, they become equal. Only for the gallium arsenide I'm saying. Okay, conduction band, gallium arsenide. So for gallium arsenide, M11, M22 and M33 are equal. Now if my M11, M22 and M33 are equal, say these three coefficient, then what will be the shape? So A, B and C are equal basically. So it becomes some constant times x square plus y square plus z square. So basically x square plus y square plus z square is equal to some constant. What is this equation? Equation of a sphere. So for gallium arsenide, it won't be an ellipse because of the symmetry of the gamma point. It will be a sphere exactly at the center. In 3D, it will be a sphere. Okay, and at the center you have the gamma point. So constant energy surface is a sphere. What about, so this is the conduction band. What about the valence band? So valence band is also at the gamma point, the valence band maximum. So for the valence band also there will be a spherical symmetry. M11, M22 and M33 will be equal. By the way, for the conduction band we have electrons as the carriers, right? So this M11, M22 and M33 will be the effective mass of the electron. For the valence band, M11, M22 and M33 will be the effective mass of hole, right? And they will be negative because of the inverse curvature like this, right? Inverse curvature will give you negative M. So this is the gallium arsenide. Gallium arsenide is a little simple, but let's talk about silicon now, which is our main material. So for silicon, where is my energy minimum in the conduction band? Do you remember? Do you recall? Where is the energy minimum for the silicon? So you may remember that for the silicon conduction band minimum, the minima will be along 100 directions. Okay, if you remember this, so this is the EK diagram drawn along a particular direction, right? So when I go from, say, gamma point, which is the origin, to x point, basically gamma to x direction, it's 100 direction. So I have written this bracket here. It means I'm talking about any 100 direction. It could be 100, it could be 010, 001. So all of how many directions will be there? 6 directions, right? 100, 010, 001, and then you have the negative also. So all of these 6 directions are equivalent directions, and along all of these 6 directions you will get an energy minimum in the EK diagram. So when I draw simply this 100, it means all the 6 directions I'm saying it will be the same for all the 6 directions, and there will be an energy minimum at some point. So this valley is called delta valley, by the way. Okay, there is a valley here. So this conduction band minimum is not at the gamma point, it is away from the gamma point along a particular direction, 100. So these are special directions along which the energy minimum occurs. So you may remember this diagram. Yes? So what is this? What is this thing? This is Brillouin zone, first Brillouin zone. Yes? Now silicon has kind of an FCC structure, a diamond structure, but 2 intervened FCC. So the reciprocal lattice, what will be that? It's BCC. So Wigner seed cell, if I draw, so that will look like this. Okay, the Wigner seed cell will look like this. So this is the gamma point at the center of the Brillouin zone, and this is my x direction. So this direction is what? 100, right? This will be some other direction, 010. Similarly, you can have 6 directions. This, and then 3 negative. Okay? And along every direction you have one point, delta point, at which you have minimum. So constant energy surfaces, it won't be just one surface, because there are 6 equivalent minimum energy points. So you can draw 6 constant energy surfaces around these points, and they will look identical. Okay. Now because of the directional nature of the minimum is not occurring at gamma point, minimum is occurring along a particular direction. So you don't have that much crystal symmetry right now. So you had perfect crystal symmetry at the gamma point, but if you go along a particular direction, you don't have that much symmetry. So because of that, it won't be a sphere. Okay, it will be again an ellipsoid. So for the silicon, the constant energy surfaces will look something like this. So you have 6 ellipsoids along 6 directions, right? 1 0 1 0 1 0 0, blah blah blah, and they all look like ellipsoid. Okay. Now along this direction, this is elongated, and if you go along, say, this direction or this direction, right? So you have this longitudinal direction, and you have this transverse direction here, and also a transverse direction along this line. So this is the third axis, right? So these 2 curvatures are equal. Now there is some symmetry here. So you have a longitudinal direction, but perpendicular to that longitudinal direction, you have 2 transverse directions. So they are definitely equivalent, you can say. So what you have for the silicon, your 2 coefficients are equal, B equal to C, but it is not equal to A. Okay, so what you can say, corresponding to B you have M22, corresponding to C you have M33. So M22 is equals to M33, but it is not equal to M11, because this A corresponds to this longitudinal direction, and B and C correspond to this direction and this direction, right? So you have 3 directions, K1, K2, K3. Okay, so M11 which is along the longitudinal direction, so that's called longitudinal effective mass. Along this direction or this direction, this direction, all of these are longitudinal masses. And let me denote that by ml. So m11 becomes ml star. Okay, because it's along the longitudinal. And m22 and m33 are also called transverse effective mass because they are perpendicular to the longitudinal direction. So this is called transverse effective mass, and both of them are equal, and combinedly they are denoted by mt star. T stands for transverse. So you have ml star and mt star. Longitudinal effective mass, transverse effective mass. Now, what will be the relationship? So because I'm talking about, say, conduction band minimum, okay, of the silicon, so that E naught becomes EC. EC means the conduction band H, the minimum of the conduction band. Okay, and you have AK1 square, and these two are equal, so B into K2 square plus K3 square, and then correspondingly you can write in terms of the effective masses. So you have ML star here, MT star here. Okay, now let's look at this ellipsoid more closely. So you have this basically. So this is ML star along this. Now this axis is not ML star, but ML star is related to the length of the axis. We saw that, right? So larger is this axis, larger will be your ML star. And then you have two equivalent directions, K2 and K3, which is MT star and MT star. Okay. So if I want to say relate the length to the ML and MT, so then we can do again the same thing that we did. So 2 ml star into E minus EC by H square is equals to length of axis of revolution of ellipsoid. So this, the major one, and the square of that, right? And 2 mt star into E minus EC by H square, that will be the width perpendicular to the axis of revolution. So this is the axis of revolution of the ellipsoid along which the ellipse can revolve, right? And perpendicular to that, this or this, the square of that length, that is related to the MT star. So you can clearly now see that if my MT star increases, this will increase, ML star increases, this will increase. Got it? So two effective masses, longitudinal, transverse, for silicon conduction band. I'm only talking about conduction band. What about the valence band, by the way? Silicon valence band. How will it look like? Will it be an ellipse? So how is this band diagram? So valence band is here. Conduction band is away from the gamma point, but the valence band is still at the gamma point. So you will still get the sphere. For the holes, it will be a spherical surface. But for electrons in the conduction band, it will be ellipse. Got it? So now let's look at some effective mass values. Now I have three materials. We only talked about these three materials. Very important: germanium, silicon, gallium arsenide. And you can see the ratio of the effective mass to the actual mass of electron, actual rest mass of electron. So this m naught is the rest mass of electron, and ml star is the longitudinal effective mass. Similarly, mt star is the transverse effective mass. So for the germanium, you can see, germanium is also not the conduction band minimum of the germanium is also not at the gamma point. So that's why you have this ml star and mt star, right? Because otherwise, if it was at the gamma point, so you won't have longitudinal and transverse, because then it will become a sphere. So then it is just the effective mass. But whenever you have away from the gamma point, so you will have M11, M22 and M33. Okay. And in germanium and silicon both, because of the symmetry, you get longitudinal and transverse, only two. So you have this value, right? So this longitudinal mass is larger than the rest mass of electron. You can see 1.588, the ratio. But for the silicon, it is 0.91, slightly less. It depends on the material. Just want to throw some numbers in front of you. And for the gallium arsenide, it is missing. Why it is missing? Because M11 is equals to M22 is equals to M33. So there is no longitudinal effective mass. There is just an effective mass. Got it? So for gallium arsenide, you have Me star. Me star means the effective mass of electron. That's it. And you have 0.067, actually much less than the actual mass of the electron. Right. So empty star is again this 0.1905. So these two values are usually you will find at several places these two values being used, because silicon is the most important material for us. And for the holes, you can see, now for the holes you have three types of effective masses: MHH, MLH, MSO. What does this mean? Let's go back a bit. You see this. Now you have one branch. Actually, these are two branches. They are overlapping. Okay. So there is one branch and there is also a second branch here. And then you have this another very distinct branch. So at the same gamma point, you have actually three branches. Depending upon their curvature, so you have a branch like this. And then you have this, which is very close to this. Okay, then you have a branch like this. And this is your gamma point. Now, because this curvature is not that much, right, compared to this curvature, and this is even more curved. Yes, so you have three different effective masses for the holes. Okay, three different effective masses, because there are three different curvatures at the gamma point. So these two are overlapping at the gamma point. It means the maximum energy point for these two bands, they are at the same point. Yes, and this is a little away, so this is called split off band, split off branch, because this is a little away. So holes can still be there, but of course most of the holes will be here. So holes try to stay at the maximum energy point. Electrons try to stay at the minimum energy point. So larger is your point in the energy, more will be the hole concentration around those points. So these will have most of the holes, but some of the holes may also be here. Okay. So all of these three are important, but because this is a little split off, so sometimes we just simply ignore this and only consider these two. Right. So now you have this and this. So one of them will be larger, one of them will be smaller. So which one is larger is called MHH, heavy, right? And the lighter one is called MLH, light hole. Heavy hole, light hole. And then you have split off. So that's why you have three effective masses. Heavy, right, which has the least curvature, because inverse of the curvature is proportional to the effective mass. EK curvature I'm talking about. And then you have light hole, and then you have split. And for all the three materials, you get all of these values, because for all the three materials you don't get ellipse. For all the three materials, the maximum energy point is at the gamma point. So all of them will be sphere. Yes, but instead of one sphere, you have three spheres actually. So one corresponding to hole, this heavy, one corresponding to light, and one corresponding to the split off. So that's why you get these, all of these columns are filled. Now with that, let's now talk about a very important topic called density of states. Now you will encounter this throughout if you stay in the semiconductors, right? So density of states you will encounter many times. It's an important material property. How do we evaluate the density of state? What is the meaning of the density of state? Okay, so let's say you have this EK diagram, 1D EK diagram. Okay, now for this energy I have this particular K value. Let me go a little larger in energy and say this is dE. Okay, and this will become E plus dE, right? And correspondingly, let me have another K. So I have this K and this K, and this is say small difference dk. Okay, now you know that the k points, although it looks as if it is continuous, but they are not continuous. They are actually discrete. Yes, in the block theorem we applied the periodic boundary conditions and we saw that k is a discrete number. Integral multiple of what? 2 pi by the dimension of the sample. If it is 1D, so it will be 2 pi by L. L is the length of the sample. So that's the distance between the two k points. It's a very small spacing. So within this dk, you can have several such k points, which are 2 pi by L distance apart. So if I zoom it out, so there will be several k points. Yes. So density of states is related to how many k points are concentrated at a particular k value or at a particular energy value. Okay. So if I go from say E to E plus dE, and k goes from k to k plus dk, so within that dk it could be that there are a lot of states. So one k point is one state, yet there are a lot of points, but at some other energy it may not be that dense. There are, say, the states are sparse. The number of states between the dk interval, it may not be that large. So this is the density, right? At what energy you have how many k states, how dense it is. So that's the density of states. Now formally, mathematically, how we define it? We define it as, so you have say within this dk, say you have dn number of states. Okay. So density of states is defined as number of states per unit energy per unit the volume of the sample. So per unit energy means dE and per unit volume of the sample. If it is simply 1D, it will be length, in 2D it will be area, in 3D it will be actual volume. Okay, so that's the density of state, the mathematical definition. You get the state, count the states, divide by the energy interval, this dE, and then divide by the volume. Now 1k state can also have two spins, up spin and down spin, so you need to multiply by that 2 also for electrons as well as holes, right? Okay, so the density of state, if I write now the formal definition, so you see number of allowed k states between energy E and E plus dE, which is basically your dN, right, divided by the volume, which is V. This 2 is because of the spin, and instead of writing dE here, I have just multiplied it here. So GE is equals to 2 by volume into this number of allowed states between E and E plus dE. Or you could have simply written it as this also, no problem. Okay, so this is the definition. Now we have to calculate the density of states for say different constant energy surfaces. I mean, depending upon the material, you may have different constant energy surface. Why I'm talking about the constant energy surface and what is the importance of that in the density of state calculation, it will become clear in a moment. So let me first talk about the density of state of electrons in 3D for spherical constant energy surface, right? For example, say gallium arsenide. So for that type of material, when the constant energy surface is spherical, so let's calculate the density of state. It's basically, it will have isotropic effective mass. Okay, so how will my spherical constant energy surface will look like? So it will look like this. Okay, so you have a sphere, and the relationship will be between E and K, it will be E is equals to E naught into H square by 2 M E star because m11 equal to m22 equal to m33, and the common factor is this, so k1 square plus k2 square plus k3 square. So in general, let me write this k1 square plus k2 square plus k3 square as some k square. Okay, so you can also say that k is the vector sum of vector k1, k2 and k3. It will give you the same thing. So E is equals to E naught plus h square k square by 2 me star. K square is the combination of these three. Now in this equation, so you have this equation, E is equals to E naught plus h square k square by 2m. In this equation, of course it will be, the spherical energy surface. But what will be the radius of that? Radius is basically under root of k1 square plus k2 square plus k3 square. That's the radius. Yes? That's the radius. If you draw a sphere, it will be under root of x square plus y square plus z square. In 2D, it will be under root of x square plus y square. Yes. So this k is the radius of this sphere, if you draw this surface. Now, for E is equals to E, you have one sphere. Let me increase this E by dE. So for E plus dE, you will have another sphere with a different radius. Yes? So this outer one is corresponding to E plus dE, and it has a little larger radius because you increase the energy. So if you increase the energy, you will increase the radius. You can see it. So k is the radius. If you increase this, so k will increase. Okay. So now you have two spheres, and in between them you have a spherical shell. Yes. What is the width of that shell? It is dk. So this is k. The inner sphere has a radius of k. The outer sphere has a radius of k plus dk, corresponding to E plus dE. Okay. So this is dk. Now what I want to find, so I know that all the points in this shell are between energy E and E plus dE. Yes? All the points in this shell are between the energy E and E plus dE. So if I want to calculate, say, the density of states, what do I want to find? I want to find how many k points are there in this shell, the number of k points in this shell, and then I will divide that by dE, and then I will divide by volume. So I want to find those number of k points that are lying between these two shells, these two surfaces, and basically this shell. How do I find that? Again, you know that number of k points are not continuous, so it's not that there are infinite number of points between this shell. Okay, they are discrete. How to find the volume associated with one k point? So you remember the difference between, say if I have 1D, distance between the two k points is 2 pi by the length. In 2D, you have this, you have a grid. We talked about it. Yes, and say along this the dimension is, say, L1, along this the dimension of the sample is L2. So this distance will be 2 pi by L1, and this width will be 2 pi by L2. Now each of these small square, this corresponds to one k point. So if you can count the number of these small areas within a given space, you can count the number of k states within that space, because one area, the small area, is associated with one k point, right? Actually it is sharing, so at each intersection you have a k point, but one square is sharing 4 such points, 1, 2, 3, 4, but only 1/4 of one point is there in one square. So that is why one square corresponds to 1 point. In 3D, it will be a small cuboid, very small cuboid. And what will be the volume of that? So you have 2 pi by L1 distance here, 2 pi by L2 distance here. So this small area will be multiplication of these two. In 3D it will be 2 pi by L1, 2 pi by L2, 2 pi by L3. Length of the sample can be different in different directions. And volume of that small cuboid will be 2 pi by L1 into 2 pi by L2 into 2 pi by L3. Yes? So this is the volume. 2 pi cube divided by L1, L2, L3, and L1 into L2 into L3 is what? Is the volume of the sample. So basically 2 pi cube divided by L. Actually we have already talked about it before. Right, so this is the volume of that small cuboid. Now I want to know in this particular shell how many such small cuboids are there. What do I do? If I divide the volume of this shell by the volume of one cuboid, one small cuboid, I will get the number of cuboids within the shell, and I will also get the number of K points. Okay, so what is the volume of this shell? What's the volume of this shell? Volume of sphere is what? So one is that you can subtract the volumes, volume of the bigger sphere minus the volume of the smaller sphere, and then you can assume that the width of the shell is very small, so you will neglect certain terms and you will get this 4 pi k square times dk. Or you can simply assume that your inner sphere is 4 pi k square surface area, and then you are going dk width. So 4 pi k square into dk width will give you the volume of the shell. You can do this exercise yourself. Okay, so the volume of the shell is 4 pi k square dk, and volume of one cuboid is 2 pi cube divided by volume. If I divide these two, what do I get? I get this 4 pi k square dk divided by 2 pi cube and into the volume. So these are my number of K points between E and E plus DE. Now I have this. What do I need to do now? I will divide this by DE. Okay, and then by the volume. So let's do that. So using this GE definition, what do we have? So 2 is for the spin again, and this is what the number of K states are divided by DE and divided by volume. And this was already there. So this cancel, and then you get dk by DE. Now E versus K relationship you already have. You have this E is equals to some E naught plus H bar square, K square divided by 2 ME star. So from this you can calculate dk by DE, and you can plug that dk by DE here. Okay, and again this K square is also related to the energy. So if I calculate everything in terms of energy, dk by DE as well as K square, so what you get? You get so you have this K, and then you have dk by DE like this, and finally you will get density of state as this expression. Okay, so this root dependency is coming because of this. Okay, so G we see in 3D, when it's a 3D semiconductor I'm talking about, that is some coefficient, some constant times under root of E minus E naught. So it has a square root dependency on the energy. It means if I increase my energy, if I go higher in energy, my density of states increases. Yes, that's what I was talking about, that the number of states which are lying at different points, they may not be the same. At some place you can get a denser density of states, some place you have a more sparse states. So as you go higher in energy, density of states increases as under root of E. So this expression we will be using again and again when we go to say devices, say for the PN junction or maybe MOSFET. This will come back. Now what is this? So this also depends upon the effective mass. So larger is the effective mass, larger is the density of states. You can see. Okay. If I plot G versus this, so it will look like this. G as a function of E, and this point is E naught, and this is like a quadratic relationship, square root relationship, sorry. Okay. Now this is for the electron in conduction band. For example, gallium arsenide is a good example. What about holes? So for electrons, this will G becomes GC. C stands for conduction band. GC as a function of energy will be the same expression, and this E naught that you see, there is this factor minus E naught becomes EC. EC is the conduction band edge. So you have, say, this is valence band, this is conduction band. So this is your EC and this is your EV. Okay, what about when I write the density of state for the this valence band? So there is the constant energy surface for valence band. For all the three materials that we saw, it was spherical. Yes. So the same expression will also hold there, but you will have to be a little careful here. So this E minus E naught will becomes under root of E naught minus E, because now you are going below this energy. You can't go above this energy. That will make the under root negative. Okay, so if you do the whole exercise again, so it will come out to be E naught minus E, or more specifically, E naught is EV here, EV minus E. So your GV, it will be proportional to this thing, and this ME star will become MH star. Okay, this ME star will become MH star. Of course, if you have heavy hole, light hole, then we will have to do some more treatment. For silicon, we will have to do something more. So now let's talk about the conduction band density of state of silicon. We've seen for a more simpler case for a sphere, but silicon has ellipsoidal constant energy surfaces, at least for the conduction band. For those surfaces, it will be a little different treatment, but eventually you will see that whatever we did for the spherical one, it will be very helpful for us even in this case. So for silicon, I know that the E can be expressed in terms of K1, K2 and K3 using this equation. So you have one longitudinal effective mass and two transverse effective masses, and denoted by empty star. Now, how do I handle this equation? Because in case of a sphere, it was easy. It was simply, because K1 square, K2 square, K3 square all had the same coefficient. So you took the coefficient out, and that became K1 square plus K2 square plus K3 square, that became K square. And that became the radius of the sphere. Yes, what do we do here? Can't be done in the same way. But what we can do, we can tweak our coordinate system a little bit. What we can do, we can define a new coordinate system in which this K1 dash is K1 by under root of ML star, and K2 dash is K2 by this under root of empty star. Similarly, K3 dash is K3 by under root of empty star. So if I define my new coordinate system by K1 dash, K2 dash and K3 dash, I can express this equation in a very simple form. So plug this K1 square as K1 dash square times ML star, so that ML will get cancelled. Similarly, for K2 and K3, empty star will get cancelled. Right, so what do you get? You get this K1 dash square plus K2 dash square plus K3 dash square. And again, your equation is very similar to what you got in a spherical case. Yes, so in this coordinate system, the same relationship between E and now K dash, that becomes the relationship of a sphere. Yeah, this is an equation of a sphere, but in a new coordinate system. And the radius is not the K square, but it is K dash square now. So combinedly, I can write under root of K1 dash square plus K2 dash square plus K3 dash square as K dash. Yes. So new coordinate system, and now I can do the same thing again. Yes, so whatever we did still helpful. So for a given energy E, so this is equation of a sphere, and if I go from E to E plus dE, the radius of square will change to k dash plus dk dash. Yes, this. So this is k dash, and the new coordinate system is k1 dash, k2 dash, k3 dash, right? The sphere is, the radius is k dash here, and for the outer one it is k dash plus dk dash. You get the point? Yes? So now we go along the same lines. Calculate the volume of this spherical shell. What will be that? So that will be 4 pi k dash square dk dash. Yes? I need to know what will be the volume of the small cuboid that corresponds to 1 k dash point. Yes, for that I would want to know what is the spacing between the k dash points. So for the k points, it was what? 2 pi by L1, 2 pi by L2, 2 pi by L3 for k1, k2 and k3. For k1 dash, k2 dash and k3 dash, what will be the spacing? It will be same, right? So this k1 dash has, so k has 2 pi by L1 spacing, but k dash is defined by k divided by under root of ml star, so the spacing will become this, divide by ml star. Similarly for k2 dash the spacing will be this, and for k3 dash the spacing will be this. Now you can multiply these three and you will get the volume of the small cuboid corresponding to 1 k dash point. Yes, and I know that 1 k dash point uniquely corresponds to 1 k point. Okay, because you have simply multiplied, simply divided k1, k2 and k3 by some numbers. So 1 k dash corresponds to 1 k point. So there is 1-to-1 equivalence still. So volume of the cell is this. You can multiply. Now in addition to 2 pi by cube by v, you will also have these masses here. Okay. And what will be the density of state? So density of state definition is this: number of allowed k states between E and E plus dE, but 1 k states correspond to 1 k dash state. So you can simply replace this thing by the number of k dash states between E and E plus dE. Okay. And one more thing, for the silicon, you don't have one ellipsoid, you have 6 of them. So if you want to count the total number of k states, so there will be a multiplication of 6. Yes, because there are 6 such ellipsoids. So those shells that you are having, it is not one shell, you have 6 such shells, and you will have to count the number of states in each such shell, and all of them will give the equal number of states. So you can simply multiply by 6. Yeah, because they are identical, all the ellipsoids are identical. So then what will be my GED? GED will be 6 into 2 by V. Number of allowed, instead of k I have k dash states here between E and E plus dE. Now what is this number? This number can be calculated by dividing the volume of the k dash shell with this volume. Okay. So you have this here, and divide 4 pi k dash square dk dash. This is the volume of the shell divided by this 2 pi by cube, and this goes in the numerator, this goes in the numerator, this v we will cancel, and you are left with this thing. Okay, so additional factor is this here. Now as we did for the spherical case, you know the k dash square in terms of energy, you know dk dash by dE in terms of energy, and eventually what you get a very similar formulation, but there is a multiplication factor difference, and which is this. And of course you have a 6 here because of the 6 values, 6 ellipsoids. So this is the expression of the density of states of silicon. Still you have under root of E minus EC dependency for the conduction band. Of course, the ellipsoids we are talking about is for the conduction band. For the valence band, you already have a sphere. Okay. Now what we can do, I would still like to use the same formula that I derived for sphere. Okay, I don't want to go from say sphere to spherical or sphere to say ellipsoid. Say if I want to use the same formula as I used for sphere, what should I do? What I can do, so instead of this thing, what did I have? Look at your spherical formula. So instead of this, you have something like m star e to the power 3 by 2. Yes. So what I can do, I can simply replace this thing, this whole thing, with this. Let me call this thing as some mn star to the power 3 by 2. Okay. And what is this mn? This mn is called density of state's effective mass. Okay. Now this equation will have the same form as you had for a spherical surface case, but you have replaced your 6 under root of ml star into mt star with one single mass. That's also an effective mass, but it is called density of state effective mass. A new quantity we defined. Okay. So it is as if, so you have 6 ellipsoid, and of course they are ellipsoid, but you still want to combine all of that into one spherical shell. So then what you can do, you can replace all of this by one sphere if you replace your 6 under root of ml star into mt star by mn to the power 3 by 2. So that's why mn is called density of state effective mass. Okay, so you can still use the spherical formula. So what is my mn? Mn is, of course, you need to take the 2 by 3 here. Okay. Now this is for silicon. Now you say if I have a different material, so what do I do? Will you do the same treatment again? No, we know that for our common materials, it will be either sphere or an ellipse. Okay. So for such cases, what I can do, I can derive a generic formula. The generic formula is this. So in general, this mn star, density of state effective mass, can be given by this formula. So NEL, it is the number of ellipsoid surfaces which are lying in the first Brillouin zone. To the power 2 by 3, for example, in case of silicon, it is 6 to the power 2 by 3. And then you have M11 into M22 into M33. Oh, I forgot to put stars here, so you can correct that. M11 star into M22 star into M33 star to the power 1 by 3. Okay, now M11 was ML star here, and M22 into M33 will make MT star, because both of them are equal for silicon. So this is your generic formula. But remember, this is number of ellipsoids within the first Brillouin zone. If say you have an ellipsoid whose some part is in the first Brillouin zone but some part is outside, so you will only count the part which is inside the first Brillouin zone. And we will see the example. And of course, this is, what is this? So this is the geometric mean of M1 into M11, M22 and M33. Okay. Now let's look at the density of state effective mass for germanium. Now for germanium, if you look at its EK diagram, how did we find that in case of silicon it will be ellipsoid, not a sphere? Because we saw that the conduction band minimum was not at the center, it was along some special direction. In case of silicon, it is 100, right? Combinedly 100, I mean the set of all the directions, the set of all equivalent 100 directions. Yet 6 such directions were there. But in case of germanium, it is not along 100, it is along 111 direction. all the equivalent 1 1 directions that you have. How many 1 1 directions you have? 1 1 1. So look at the EK diagram here. So this is the gamma to x direction, but in the gamma to x direction if you go, so you have a valley, but this valley has a larger energy than another valley which is along 1 1 1 direction. So if you go from gamma to L, you see this is the minimum energy point for the germanium. Okay, now it is at the boundary of L. So at the L boundary you have this point, exactly at the boundary. So when you go from gamma to L, you are touching the surface of the Brillouin zone, and at the surface of the Brillouin zone you have this minimum energy point. For silicon it wasn't the case. For silicon it was something like this, little inside, right, along 100 direction but quite inside, delta point. But for germanium it is at the surface. So because it is 1 1 1 direction, so your ellipsoids are along 1 1 1 directions, not 1 0 0. Okay, but because they are touching the Brillouin zone boundary, so this point L point is here, 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 here. Okay, so only half of the ellipse is inside the Brillouin zone, not full ellipse, because it is at the surface. So half of the ellipsoid will be inside the surface, half of the ellipsoid will be outside the surface because of the symmetry of that ellipsoid. Yes, so although there are 8 such directions, the number of ellipsoids effectively that are present in the Brillouin zone are only 4, half. Okay, so when you calculate the effective mass, density of state effective mass, so NEL you will take equal to 4, not equal to 8. So then you have, M11 is ML star. Of course you have a longitudinal direction here and 2 transverse directions which are equivalent. So that's why M22 equal to M33 equal to MT star, longitudinal, transverse, but NEL equal to 4. So this is your density of state effective mass for the germanium. So you took the geometric mean, so that will make it ML star into MT star square to the power 1 by 3, and then you have 4 to the power 2 by 3. Okay, so now we have covered everything, right, about the electrons. Now let me quickly talk about the holes and then this topic is over. Density of states of the valence band. In case of germanium, it is spherical, but we did not talk about the heavy hole, light hole, or say split off, right? So you have 3 different materials, and in all of the cases we saw it will be spherical, but then there can be 3 cases: heavy hole, light hole, split off. How do I take care of these 3 subbands, I can say? Right? There are 3 branches in the EK. How do I take care of that? Split off we usually don't consider because the density of holes within that split off band will be small. So let me only consider heavy hole and light hole. Okay. So you have this. Yes. So the split off I won't consider, but then there are 2 branches. Right. Here the branches are kind of overlapping, but if you zoom it out, there will still be 2 branches, and then you have 2 branches. So in all the 3 materials you have heavy hole, light hole. So what do I do? I will have to count the number of K states within both of these branches. Okay, because the maximum for both of these branches is the same point. So you can't escape. You will have to count the number of states for both the branches. Now for one branch I know the formula. For sphere I know the formula. For if I have only one branch, I know what is the number of states. What if I have 2 branches? What do? I will have to add up the number of states because of the second branch. So basically I will have to add up the density of states because of the first and the second. Okay, if you want to calculate the total number of states. between the same energy E and E plus dE. It is like this. I think this will give you a better idea. Okay, you have this. Now say I have this energy level, yes, E, and now I have this, say, E plus dE. Say my dE is negative. Okay, so corresponding to this I have this and this. Okay, so whatever the number of states are there, so they correspond to, say, the band number 1. So I will add the density of states, so for this and this, I know the formula. I mean, this is 1D, but for 3D we already know, But within this same strip, you also have this. So who will count this and this? So you will have to add these states also. Okay, so not just for the one particular branch, you will have to add for all the branches. For 2 branches, you will have to add 2 density of states. So let's do that. So one will be heavy hole branch, one will be light hole branch. So total density of states will be density of state for the heavy hole branch plus density of state for the light hole branch. And both the branches are at gamma equal to 0. So both of them will have spheres, right? Both of them will have spherical constant energy surfaces. So for the sphere, we know what's the formula. The formula is this, but instead of M star here, I have MHH star, heavy hole, and for the light hole, I will have MLH star here, right? And of course, it is the valence band, so you don't have E minus E naught, you have E naught minus E. So EV minus E and EV minus E. That's the total density of states. Now what if I want to calculate the density of states effective mass here? As in case of electron, we calculated Mn star, which is basically you want to replace all the ellipses, 6 ellipsoids with one sphere. Now what if I want to do the same thing here? What if I want to, say, remove these 2 spheres, replace these 2 spheres with one single sphere? So that will make my density of states effective mass, right? If I want to replace these 2 with just one, with only one effective mass, so that will be density of state effective mass. So let me, on the left hand side, let me write it in this form. So my GV is equals to, say, let me define the density of state effective mass as MP star. So if it is a single sphere, so it will simply be under root of 2 by pi square into MP star to the power 3 by 2 blah 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 under root of EV minus E, right? So it's like an equivalent mass, you can say, and this is equals to obviously this. Okay, now this they will get cancelled, and other common factors will also get cancelled. So what you get is this. So density of state effective mass of the holes can be evaluated using this equation. And for germanium, silicon or gallium arsenide, the same formula works. So you don't have to worry about that number of ellipses or whatever, because there are no ellipses here. Just 2 spheres replaced by 1 sphere. If there would have been, say, split off, so what do? There will be another term here, split off to the power 3 by 2.